Hello, everybody, and welcome to the session on an attempt to understand our model's predictions. My name is Parul Pandey, and I work as a machine learning engineer at Weights and Biases, which is an MLOps platform. I'm originally an electrical engineer and also a Kaggle Grandmaster in the notebooks category. And I'm also co-authoring a book on machine learning for high-risk applications for O'Reilly. The book will come out later this year, but if you are interested to read the raw and unedited version, you can go to the site and read it. The link is on the slides. So let's first talk about the motivation to understand what our models are learning. Now, you would think as long as we are getting a good accuracy and good predictions, why should we even bother about that? Now, the thing is, these complex systems made up of neural networks and boosted trees, etc., they tend to drift towards unsafe conditions unless constant vigilance is maintained. And this is a line by Google Research itself. And to elaborate more on this line, I'll share 3 examples with you, but there are many more. So let's start with machine bias. Machine bias is basically a report which was put forth by ProPublica, which is an investigative journalism outfit. And they analyzed the scores of Compass. So what Compass is a case management and decision-making tool, which is used by judiciary. And what it does is it gives the probability of the chances of a person recommitting, reoffending, or committing a crime again, which is called recidivism. And what they found, ProPublica, what they found was that Black defendants were far more likely than the white defendants to be incorrectly judged, to be at a higher risk of reoffending. Then there's this paper by Datta et al. On automated experiments on ad privacy settings. And what this paper found out was that if in the Google ad settings, if you were to put the gender as female, then there were less chances that high-paying jobs were shown to you. And ultimately, there's an example, a very interesting one, which is from Washington Post, where they analyzed these softwares which are used for interviewing candidates. And what they found was that on the right-hand side, the photograph, or if the interview is done with a background made up of books, you get higher scores as compared to when your background is white. So these are just sort of few examples which just sort of force us to think, like, is it just enough to only focus on accuracy, or it's even important to understand what our model is actually learning? And so why does this actually happen? Why does it even happen? Why do we get such weird results and biased results? Because what we do is we just focus on the data, and that goes inside this black box model about which we have no understanding. We get predictions, and then we have a lot of confusion and doubt as to why this prediction came into being, and why did the model predict yes or no, or true, false, and so on. And so if we were to put all of these in bullet points, we can say that we need explainability in machine learning to inculcate trust in models, to debug predictions so that we can go back and correct things, to detect unwarranted bias like we saw in these examples, to ensure suitability of models for deployment. I mean, who would want to put a biased model or an incorrect model out there in the real world? And then finally, there's global AI regulation. There's regulation which expects you to get correct results and not biased results in any way. And so who needs explainability? Of course, the people who are making the models, who are working in this field, data scientists and ML engineers who work day in, day out with them, the end users who will finally use these models, and the regulators definitely, they need it. So now I think we sort of have a good idea about the motivation behind even attempting to understand the field of responsible AI. Now, let's now go a little deeper into it and understand what is technical meaning of explanations. What do you mean by this? What are the jargons or the terminologies? These are important because when we go and read, we'll go further into this field and we'll read about them more. And I hope after this session, you would want to do that. These terminology will, understanding of these terminologies will come in very handy. So let's first start with the definition. Now, there is no clear definition of what explainable AI is, but if there are these two papers which are thought to be pioneers in this field, and what the gist of these is that explainability is the degree to which humans can understand and trust machine learning models' predictions. And that's exactly what the topic of our session today is. Now, in this field, you'll often come across these two terms, interpretable and explainable, and a lot of times these are being used interchangeably, but there is a difference between them. So while interpretable models, they describe the internals of a system, right? The explainable AI means to summarize the reasons for a model's behavior. So if a human can understand the internal workings of a model, then that model is interpretable. But if the model is so complex with millions and millions of parameters, it becomes difficult to understand. But in a way, if we can summarize that model in some way that gives us things like feature importance or how the feature sort of changes as you vary, how the predictions change as you vary the features, then that's explainable AI. And we'll touch more on this later. Also, sometimes people also sort of get confused, like what is responsible AI, and then what is explainable AI, and then what is interpretable AI. So basically, responsible AI, you can think of it as an umbrella concept, and explainability and interpretability, fairness, privacy, security, they all are the subparts of it. And they are sort of hinged at some of the other points, but they also are separate different fields on their own. Now let's start with taxonomy of or some of the words or the terms that you'll come across very often. So what are the different ways in which you can explain the models? So either you could explain in the post hoc manner. So post hoc, as you can understand from the name itself, it means after the model has been trained, then you explain the model. Intrinsic, on the other hand, means you create models which are inherently explainable. So if you talk about linear regression, logistic regression, decision trees, you'll see that these models don't need any other explanations. They are themselves explanatory. Like if you see a decision tree, you can look at the tree, and if the tree isn't like too big, and then you can understand, why, we came at this decision. On the other hand, if you take a deep neural network, it has millions of parameters, and it's not possible for us to actually go and look at each and every parameter. So for such things, what we can do is we can pass them through an explainer or a post hoc technique, and the resultant is a simpler model, which then can be explained. The other way in which you can explain the model is by giving local explanations, which means you explain every individual prediction or a small part of a model's prediction space. So let's say there are 10 data points in your data set, and you can give explanations for every data point. But a global, on the other hand, means when you explain the entire model behaviors, like for instance, you say that for this model, this feature was important, and for this model, this feature was not important. So you explain on a whole. So let's look at a few examples of each of both interpretable models as well as explainable models. Now there's a huge field. This is a very big field. There are lots of examples and models out there. The new researches which are coming out every day. And I will just sort of give you examples of few of them, but then I encourage you to go and read more about it and go and look at the papers and look at some of the other techniques also which are available in the space. So for instance, there's penalized regression. So regression is something which is used a lot. And by penalizing means you put some constraints on the model, right? And you put some constraints and some optimization methods on the regression model. And so they become highly interpretable. So let's say you have lasso and you have ridge regression that you apply to regularize your models. And so what you can do is you can use elastic net, which sort of combines the goodness of both these regularization techniques of both L1 and L2. And so when you use, say, elastic net on a generalized linear model, what you get is a highly interpretable model. Then there is another, you could say, category of models called GAMs, which are called generalized additive models. And while linear models are highly interpretable, we know that sometimes they cannot capture accurately the non-linearities which are actually present in the real world data sets, right? And that's a criticism also for them. So in such case, we can use GAMs, and GAMs basically not only model the linear relationships, non-linear relationships, sorry, but they're also highly interpretable. And there is, you could say, another variant of GAMs, which are called GA2Ms or EBMs, explainable boosting machines, which is EBMs have been created by Microsoft and Microsoft Research. And EBMs are not only as accurate as the gradient boosting machines like XGBoost, etc., but unlike them, they are highly interpretable. Then we have decision trees, again, like we saw in the previous examples, highly interpretable, but they are prone to overfitting. And then another could be constrained XGBoost models. So XGBoost models on their own might not be interpretable, but they're accurate, right? So sometimes you're in this dilemma, what should I do? Should I go for accuracy or should I go for explainability? But if you were to constrain these models, by constrain, I mean, let's say there's a feature in your data set, and when that feature increases, another feature decreases, right? But when you're using XGBoost, what you see is that as that feature 1 increases, feature 2 is also increasing. But as a domain expert, you know, this shouldn't be the case. So you'll put a constraint on the models. You'll put a constraint that if feature A increases, feature B should decrease. And when you do so, you not only make the model interpretable, but you also inject your domain expertise into it, which is very, very essential in real world machine learning scenarios, because we need we need experts, we need domain experts. And when we combine the domain expertise with the machine learning ability that we have today, only then we will be able to make the real use of machine learning. Next, we'll talk about post hoc techniques, those techniques which are applied once the model has been trained. So now these are model agnostic, like you can apply them on any model. So you train your model like the way you would have done. And once you get your predictions, then you can apply these techniques. So there are a lot of examples, like we have partial dependence plots, SHAP, line, counterfactual, saliency maps, occlusions. This is for image, for text data, for tabular data, and so on. So we won't be able to cover all of them, but I'll just cover 2 important ones here. And so one of them is SHAP values. So SHAP is an acronym. It stands for Shapley Additive Explanations, and it leverages the concept of cooperative grim theory and breaks down the prediction to measure the impact of each feature in that prediction. And because this is important, we'll go a little deeper into it. So let's say I'll give an example how to understand and put it into a little context. So let's say you go out on a dinner with 3 of your friends and you order some food, and all of you order different kinds of food. Now, some of you order more expensive food, the others hardly order anything or maybe not so expensive. So when the time comes to pay the bill, you want to divide the bill fairly amongst all of you. Now, the first idea would be to just, sort of divide the entire bill by 4. But then that's not fair division, because some of you ordered very expensive things. Some of you didn't even have anything. So that's not a correct way. Another example that you could sort of take is, let's say you are working in a corporation and you're working towards a project, and then you get some profit from there. Now you want to divide that profit in terms of how much effort you put into it. So the person who's put more effort will get more percentage of the bonus, and so on. I hope you get the point. And so Lloyd Shapley, he was an economist and he won a Nobel Prize in 2012. He introduced the concept of Shapley values. And what these values sort of did was they measured the average contribution of a player. And so what do you mean by a player? So these all members who inside are called players, and they are in a coalition, a group, and they are working towards or for this value or this payout. And what Shapley values do is they tell you the contribution, the fair contribution of every member, every player in this coalition. This is in terms of the cooperative game theory. So in a game theory, you have coalition, you have players, and you have value and payout. Now, two researchers, Lundberg and Lee, they thought of putting this into a machine learning perspective. And so what they did was they said, these players could be features, the coalition is a model, and predictions is your payout. And the SHAP values will then tell you what is the average contribution of these features towards the prediction. And so that's how SHAP is related to Shapley values. And so how when you understand it, I mean, it's okay if you understand the terminologies, but then how do you sort of understand it from a machine learning problem? So there are various ways in which you interpret SHAP values, and one of them is SHAP summary plots. And so this gives you an indication of the feature importance. So the value which is on the top is the most important for the prediction of the model, and the one at the bottom is the least important. You have the colors. So the red one tells you that this value, if it's higher, then this leads to an increase in the prediction value, and if it's lower, it leads to decrease, and so on. And that's how you read these plots. And there are different kinds of other plots. You have a force plot. And so what this will tell you is how each of this feature contributes to the prediction. So which feature is more important for this model, which feature is less important. There's another technique. So while SHAP, the example that we saw here, this was giving you global view of the model, but you can also, SHAP will also help you to understand how the model is behaving locally. There's another model, another technique, a post-hoc technique called LIME. And LIME stands for Local Interpretable Model Agnostic Explanations. And as the name suggests, this is a local technique. So it can only be used locally. So again, this explains the predictions of any machine learning classifier. It's model agnostic. You can use it for text data. You can use for image data or tabular data. And it's a pretty interesting concept. So if you look at this picture on your screen, now what it does is, if you can see the boundary, so you can see that this is a very non-linear boundary, right? And if you were to see this, it becomes a little difficult to explain such a model. So you can see there are two classes. One is this pink, one is this blue. And there's a very non-linear boundary separating these two classes. But because LIME is a local technique, so we just focus on a single data point at a time. And our data point is this red plus sign. And what LIME says is, like, we just focus on this and we just sort of zoom it onto it. And when we zoom here, we see that the boundary now is more or less linear. So we're not concerned what's happening around, but we just zoom onto this data point and look around it and look in its vicinity, and we see now this is a straight line. So, how do you use line, or basically how does it work? It's that you sort of generate data points around this data point of interest, and that is this red plus, and then you give them weights. So the data points near this point of interest is given more weight as compared to the ones outside. And then you use a very simple linear model to sort of make predictions. So we won't go further into that. I just want to show you the use case or how it is used. And while it can be used for text and tabular data, I will give you a very classic example on image data. So there was this experiment done at University of Washington. They created a classifier to differentiate between wolves and huskies, right? And if you see here, huskies are those big dogs which sort of look a little similar to wolves, but they're different. And the classifier came out to be very good, and it gave you great results. As you can also see, there's just single mistake here amongst the 6 examples. It's doing a great job, right? And you would want to just go and deploy this classifier for real world if you want to create, you could say, an app to differentiate between huskies and wolves. But then they also wanted to understand how was the model differentiating between the 2 animals. So they used line. And what shocking results they got was that what the model was looking at was not the picture of the animal, but on the other hand, it was looking at the background image, which was snow. So what it was doing is wherever it was finding snow, it would always predict it to be a wolf. And if it did not find snow, it did not predict it as wolf. And that's because most of the images that were fed into this classifier had wolves which had snow in the background. And so it just picked up that thing from the images, and it picked up that feature, and then it was just making predictions based on whether the image had snow or not. And so instead of having a wolf and a husky classifier, we actually got a great snow detector. And now the important thing about here is that if we wouldn't have looked under the hood and seen what the model had learned, we were deploying a biased model in the world. And this could be true for many such examples. So this is an image which I actually borrowed from LinkedIn. So this was actually shared by Ms. Murut Durmus. And so it's everybody loves AI. It's a great buzzword. People are using machine learning to do some great work also. There's a lot of research happening in this field. But we also have to understand that we have to look at the ethical implications also. And we cannot just blindly deploy machine learning models out there, but we also have to take the responsibility for the decision of the algorithm and to ensure that they are not discriminating, they are not biased, and they are not treating anybody unfairly based on their gender, based on their race. So this was all, and this is basically just an introduction to this field. Like I said, this is this huge field out there, and it's a wonderful upcoming field, and a lot of research by different companies going on. There are a lot of open source libraries out there. For instance, for Microsoft, you have InterpretML, there is FairML, then there's Captain library by PyTorch, and anybody who's interested in machine learning and who wants to create good models should also keep an eye for interpretability and explainability, because this is not something that you can sprinkle at the end of your project just to see, okay, let me just add in a dash of responsibility just so that it appears good. as data scientists, as machine learning engineers, as people working in this field, it's our genuine responsibility to deploy things that are safe for humans and just not create things which sort of look good on paper and without thinking from an ethical or a moral perspective. Thank you so much. I hope you've enjoyed the session as much as I did delivering it. And if you've got any questions, any feedbacks, you can reach out to me on LinkedIn, on Twitter. All my socials are listed on PyCon Iran website. Thank you so much.